Okay, so welcome everyone. The first speaker of today is Steve Lowe from Caltech, and he's going to talk about optimal power flow. What's the full title? Relaxations, online algorithms, and fast dynamics.
Thank you, David. And it's always great to be back at Berkeley, Caltech too. So thank you very much, Dave Carr, for the invitation. So I talk about OPF. So it's work that involves many people, and there's 3 pieces. I might have to stop at the end of the second piece, which is fine. So I'll mention more of these collaborators in each piece. So this is a system that we look at where electricity comes from. There are, in the US, about 10 to 20,000 large centralized generation plants that generates the majority of the electricity. Then they go through a power network, eventually get to residential houses, commercial houses, and so on, which will be the plug on the wall. The difference between transmission network and distribution network is that transmission network is much longer distance and also much higher voltages. So this will be hundreds of thousands of volts. Distribution network is lower voltage. Eventually, it steps down to 120 volt here.
Am I reading correctly? How is the power plant itself less voltage than the...
So it's here in particular example is 15,000. So it's lower. It steps up to a transmission network because at a higher voltage, the network loss is lower. Another key difference is that transmission network is typically mesh network with loops, whereas in distribution network, almost all distribution network, with exceptions, are tree topology. So that turns out to be important, as we'll see later on. So both the system dynamics and the control that we apply spans a large range of timescale, from years where we do a lot of plannings to day ahead, which we run day ahead markets, for example, to hours and say 15 or 5 minutes. So real time in electricity market typically means 5 minutes. And then to under a minute to seconds, even sub-seconds. And the behavior of the network at different timescales certainly is different, and they're described by different models. So for the timescales here that we'll talk about, this will be the power flow equations. And in the third part, if we do get to that, then it's sort of a seconds timescale, then you have ODEs. And depending on how realistic you want to be, say for generator models, for example, you have different complexity of models. So we'll talk about the first and the second part will be here, and the third part will be here. And OPF, which is the problems that describes a lot of applications here, is simply a constraint optimization. And it is important because in many of those power system operations and planning problems, underlying those applications is this OPF. And therefore, it is routinely being solved for network control optimization decisions and also to set pricing, for example. At timescales, minutes, hours, days, and so on, is first formulated in 1962, well known to be non-convex because the Kirchhoff law is nonlinear. If you look at what's the most widely used algorithm, is actually linearization. So you linearize your nonlinear power flow equations, and then you get an LP, you solve it. Then the solution may not satisfy the power flow equations, and therefore you may not be able to apply them in practice. What you do then is where the engineering intuition comes in, you tweak your LP, and then you repeat the cycle. But there are many, many algorithms that people have applied to OPF problem. So the nonlinearity of power flow equations give us a non-convex problem, and you can visualize how terrible it could be. So this is a very simple example with 3 buses, 3 nodes in the network, and if you project to some variables in your optimization, then this is the feasible set.
What are these nodes? These are the power plants?
So in this particular example, there are 3 nodes. Each has a certain power plant. So this is, yeah, and then lines connecting them. So how to do with non-convexity? And power flow equation is one source of non-convexity. There are other sources such as you have to deal with discrete variables, for example. But here, I'm only talking about non-convexity due to power flow equations. So this is a non-convexity that we cannot design away. So the 2 approaches, and many others. One is semi-definite relaxation I'll talk about. And the second idea, separately, the second idea is using the grid as the implicit power flow solution solvers. So this is the online OPF that I talk about. So the first, right? So the first part is semi-definite relaxation, the work that has been going on for the last few years, and then the second part. So it defines the model. I'll just give you a sense of where the computational challenge is and some of the results. But it mainly serves as a motivation for the second part, which is online OPF. So both are slow time scale problems. And then if we have time, we can extend the idea here to a fast time scale problem, which is low side frequency control. All right, so the first part. Many people have contributed to this, and here are some of them. Both used to be a graduate student at Caltech, Professor Manny Chandy. For Riva, also a graduate student at Caltech. Lin-Wen was a graduate student at Caltech, and Javad Lavia here. I was John Doyle's student. All right. So the problem, again, is you want to minimize a certain cost, examples of that, subject to two generation limits. Okay, right. Okay. Let me just show the mathematical one. Subject to certain constraints, basically. And so the variable is the complex voltage phasor at each node in the network. So VI is a complex number, and C, the cost matrix, is complex, and then Yj depends on the network. So Yj describes the network. It gives both the network topology, but also impedance on the lines. And this, typically, we assume this is positive definite, and therefore, the objective function is simple. All the complexity in this particular simple formulation is in this powerful equation. So Yj, one for each node j, is not even Hermitian. It's not PSD. And powerful equation describes that at each node j, Sj is a complex number that represents the real power and reactive power, imaginary power, at node j. So this could be, let's say j has a generator, that it generates real power and imaginary power. So you can think of it in the phasor domain, each power has two components. And you can map it to physical meanings. But each power, let's say j is a generator node, then it generates the real and reactive power, the complex pair number, must equal to this. And this simply represents Kirchhoff's law. And it says at every node j, power must be balanced. That's all it says. But it's quadratic in the variable v. That's the important piece. Right. So Yj, one for each j, is a n by n matrix. And this is Ren 1 matrix. So this is an n by n matrix. You take the trace, the sum of diagonal terms, which, because this is not Hermitian, is a complex number, this must equal to the power injection at node j. If j is a load, then this is basically typically take negative values for real and reactive, real and imaginary parts. So the equality, you just have the equality. So Sj, if you think of this as a generator, then this inequality simply says the generator has a certain capacity, lower bound which could be 0, and some finite upper bound. And then this constraint says that the voltage magnitude must be within, say, 5% of its nominal value. So 120 volt here, plus or minus 5%. So that's the basic structure of OPF. It's non-convex, again, because this is non-convex, and therefore you get a QCQP. A standard way to deal with this is to do SDP relaxation. So it looks like this. This is the problem we have. This is the OPF, and this is where the non-convexity is. This is also non-convex, but this is the same form. You can write this form in the same form here. And the thing to note is that everywhere the variable v appears, it appears as VVH, a Ren 1 matrix. And therefore, you can think of this matrix as a variable and write an equivalent problem, just replace VVH by the matrix W. So this is n by n complex matrix. Except that it's not arbitrary n by n matrix. Matrix has to be positive semi-definite and Ren 1. But the important thing to note is that while this is quadratic in V, this is linear in the variable. So Kirchhoff's law is linear in this matrix variable. And this is convex constraint, and this is the only non-convex constraint. And SDP simply says, let's ignore Okay. So, and therefore, if you look at the so the two problems are equivalent in the sense that there's a one-to-one mapping between the feasible sets. Given a V, you can write a W that's set by these set of conditions. And given a W that's set by this set of conditions, there's a unique V that was set by this set of conditions up to a rotation. And therefore, you can characterize the feasible set which for the OPF by this set in W. Right? And this is only non-convexity. If you ignore this, and therefore you minimize your cost, not over this set, but over this set without RAM 1. Then you get a convex problem, it's SDP. You solve for optimal solution. And then you check whether your optimal solution W star turns out to be RAM 1. If it is RAM 1, then you can obtain an optimal V for your original convex problem. So this is great, except that this solves for n variable, n complex variables, and this is n squared. So we would like to be able to reduce that, and here's one idea. So this is SDP. If you have a network with 5 nodes, then we solve for 5 by 5 complex matrix. But if we look at the Kirchhoff law, right? So Kirchhoff law says this trace equals some Sj. If you expand this, then you see that this is non-zero only at off-diagonal entries when, let's say, 1, 3, when there's a link between node 1 and node 3. If there's no link between I and j, then this expression doesn't depend on wij. And therefore, you can think of what's called a partial matrix is simply a set of complex numbers that corresponds to the entries for which you do have a link plus the diagonals. And therefore, the number of variables here in the partial matrix is not n squared, but n plus 2n. And for typical network, m is much less than n squared. So for attribute test system, benchmark system, for example, m is no more than 1.6n, for example. So it's some linear in n. And therefore, for last network, this is much, much smaller problem.
Are these graphs typically planar graphs?
Surprisingly, not necessarily. It's not clear why. One reason is perhaps it's like what Edward Lee was saying. There's a physical network, a physical system, and there's a model. The actual model that people use even for attribute benchmark systems, typically, they are transformed. So you take a physical network and model it, and then you get a messy graph, and then you do some transformation, get a simpler one. Perhaps during that transformation, you get this. All right. So, okay. So how do we describe okay. So how do we describe the feasible set OPF in terms of the partial matrix WG? So the describe we do it for SDP is we establish a one-to-one mapping between V and M by M matrix, so that this satisfies the quadratic equations, these satisfy linear equations, but then you require this. Right? So if you want to describe V in terms of the partial matrix, you not only replace W by WG, which is a partial matrix, but also the simplicity comes here. You don't require the entire W to be positive, semi-definite, and RAM 1, but only for every line that connects node J and K, you have this 2 by 2 matrix. So WJJ, WJK, WKJ, WJJ. So 2 by 2 matrix. You only require those 2 by 2 matrices to be PSD and RAM 1. So you have as many as number of lines, but each is much smaller piece. But then you require the cycle condition. There's some condition on this WG, the set of complex numbers. The cycle condition, the only thing I want to point out is that if you look at these two conditions, these other conditions are local in the sense that each equation involves variables at 2 ends of a line. Same here, but this is global. The cycle condition is global. It depends on the variables on the entire cycle. And that has a lot of complexity. And then you can show that indeed all 3 sets are equivalent in the sense there's a one-to-one mapping among them. All right. And therefore, given any partial matrix, there's only one way you can fill it. You can complete the matrix up to a rotation. And then you can map it to the voltage. OK. And therefore, we could, instead of minimizing cost over this set, we can minimize the cost over this set. And then once we get an optimal solution, we can check the condition. We can check whether each 2x2 matrix is PSE and RAM1, and also satisfies cycle condition. If it does, then we can obtain a global optimal solution. Otherwise, we're stuck. Except that this is also non-convex. But if you look at where the non-convexity comes in, is where the RAM1, this is 2x4, 2x2 matrices, and also cycle condition. So the natural thing to do is just ignore them. Then you get SOCP, much simpler, orders of magnitude faster, typically, for large networks. OK, and therefore, right, and if the network turns out to have tree topology, radial network means it's a tree topology, then SDP relaxation and SOCP will be the same, same tightness. If meshed, then you'll be strictly, SDP will be strictly tighter. OK, and therefore, for we call that almost all distribution systems, which are probably where most of the smart grid innovations will first appear, are radial, are tree topologies. And therefore, for them, never solve SDP, just solve SOCP. And therefore, the strategy is, instead of solving OPF, you solve the relaxation, and then with an optimal solution of the relaxation, you check some conditions. If it is satisfied, then you're done. OK, so and therefore, it is important that we can do this and we'll get a optimal solution that satisfies conditions. Of course, there's no guarantee, except that if the network is a tree, then people have developed sufficient conditions that will guarantee this strategy will work. Now, empirically meaning that people try many actually test systems and some data from utility companies and so on, very often you will get optimal solutions, even when the sufficient conditions are not satisfied. So somehow practical network seems to have nice structure. OK, so here's one class of conditions, sufficient conditions that will guarantee SOCP relaxation will always be exact for tree network. So in general, we have this QCQP, and OPF is just one example of that. And it's characterized by the set of cost matrices and constraint matrices. And for this example, the bounds, the bounds don't matter. There are other conditions where the bounds are important. So the key condition is the following. So you look at the set of matrices, take any two nodes that are connected. So you have an ij, a line between I and j, so you get k+1 complex numbers. The magnitude of these complex numbers are not important. You just care about the phase. So you can plot them on this unit circle in a complex plane. If all those numbers lies on a half plane, any half plane through the origin, so you draw a line through the origin, if you can find a line such that all those k+1 complex numbers lies on one side of the line, you could lie on the line, then SOCP relaxation will be exact for tree network. OK. The implication, so that's for general QCQP. The implication, you map it to OPF. Then it has something to do with, remember that OPF has this constraint on the voltages and also on, say, the injections. So the generation limits, for example, or the low limits. You are doing demand response. There's a certain limit you can do your optimization over. So those limits. So that condition has implications on what those limits can be. Right? It turns out for this condition, the voltage limits do not matter. It's the upper or lower bounds on the generated limits or low limits. And then there's some other conditions where the bounds on the generation low limits are not important. It's only the upper bound on the voltage important. OK, so here's a pictorial illustration where in this particular example, the feasible set in OPF is this black curve, which is non-convex. When you do SDP, you basically get a convex, roughly a convex hull almost of this the purple region. And if you do SOCP, then you get this yellow region, which is strictly larger. And when it is exact, what happened, say in this particular example, is so this is a mesh network, but it turns out to be exact, is that the boundary of the purple region, SDP feasible set, coincide with this black curve, the original feasible set. And therefore, if the cost function is the level sets here, then when you minimize over the purple region, SDP relaxation, you will get an optimal point that lies on the black curve, and therefore you get an optimal solution.
Stephen, this YJ matrix, Y matrix, which was capturing network topology and impedance.
Right. One for each node. That's actually not the admittance matrix, but it depends on the admittance matrix.
Right. For a given topology, can you change the impedances by, say, adding extra capacitors or on top of the network topology that's given to make the problem more amenable?
As a part of optimization variable, right?
No. I mean,
when you design.
Yeah.
Yes, so there are capacitor banks you can do, but then the capacitor banks will be attached to the nodes. There are also new technology for electronics where you can change the line impedance. That's perhaps what you're referring to. Yes, then you can do that. Now, if to the other extreme, if you assume there's potentially a phase shifter that allows you to change the phase, it's like the similar effect from capacitors, right? On every line, then the sufficient condition that holds only for the radio will hold for the mesh as well. And now it turns out you don't need to have an adjustable phase shift at every line in the network. You can take any arbitrary spanning tree on the network. You can optimize whatever criteria and pick a spanning tree. You only need no more than a phase shifter at each line not on the tree. So since the network is sparse, is typically a small number, but still, it's not practical yet. It could be in the future. So no one is going to install phase shifter in order to get a convex OPF. Right. Now, but yes. Okay. So there are many questions one can ask. So you can characterize different relaxations and relationship among them, and then there are also different power flow models and the relation among them. And then you can look at under what conditions they're exact. What if the first order relaxation is not exact? Then you can go up the polynomial optimization hierarchy and try to tighten the relaxation at the cost of computational complexity. There are also nonlinear techniques you can apply. You can look at many applications on top of this. So if you're doing demand response, EV charging, or even economic dispatch, power market power analysis, and so on, you can use you can ask those kind of questions. You can also say, let's assume the relaxation is going to be exact. We can just solve convex problem. Then do we have an easier way to come up with distributed algorithms for OPF, and so on. And then you can apply, you can extend the theory to multi-phase unbalanced networks and so on. Okay.
Question?
Yeah.
How many of these approaches would you consider practical that have a chance of being adopted in real?
Right. So there's certainly many things you can pose here that can potentially be adopted. For example, I can do EV charging, you work with utility. So what is practical being adopted depends on whether the technology is easy, meaning that it's reasonably cost to implement and so on. But the bigger hurdle is you have to convince, let's say you want to do EV charging, but also try to co-optimize with a grid asset. You need to work with the utility. So that's usually the hard part, much harder part than the technical part. There are also economic dispatch. Right now, people use what's called DCOPF. Simply, you solve the LP, the linearization. FERC and also some other people is trying to push very hard to have ISOs to use ACOPF to solve their economic dispatch. So certainly there are computational technical challenges and all of that, but the much bigger hurdle will come is actually to convince the industries and all of that. So so some people told me that their expectation that it would take 10 years. So those are non-technical hurdles. So I think some of the techniques, there's no great technical barrier. Is the same thing if you develop something that is, you prove a great theorem, and develop a new great algorithm, moving into practice can be much bigger.
And if let's say some of those are adopted in practice, do you have any?
How much benefit? How much benefit?
Approach over the linearized.
Right. So again, there doesn't seem to be consensus. There are people who said there won't be much difference. There are people who believe there can be huge. So Ferd estimate that if you just do economic dispatch on ACOPF, you can probably save between 2 to 10 billion per year. Is that big enough? It's free money after development. So it's not clear. It certainly depends. Sean probably has some opinion too. Yes?
I mean, this might be a very stupid question, but how do you physically control flow in?
Right, okay, so.
Do you have things equivalent to queues?
So one of the major difficulties with electricity network is that there's no large-scale inexpensive queues, energy storage in the network. And therefore, supply-demand needs to balance every point, every time of the network. Unless you are like Norway, 90% hydro.
Sorry, so then I had a follow-up question to that. You have to continuously solve the equation because demands are changing pretty rapidly, right? So how do you update your solutions as demands change?
Right, okay. So there's a long answer we can take offline. But the quick answer is that, again, it depends on the application you look at. Economic dispatch, for example, that you solve for markets, that's solved every 15 minutes. And therefore, you roughly schedule your generation. Now, and then you hope that it's roughly balanced. And then the small thing, then there are other mechanisms that will deal with it. OK, so the second part, online OPF. So again, Gan used to be a graduate at Caltech. DJ, who was a postdoc, is actually joining PNL this week. And DJ Tan, who's graduating at Caltech. Okay, so the motivation. So if you look at the two biggest networks, the communication network and the communication network and the power network, both started about 130 years ago in a very similar engineering, economic, regulatory structure to provide a single commodity extremely reliably. And both went through great developments through the wars, post-wars and everything, even started to deregulate around, not surprisingly, that was the political time. Many things got deregulated around the same time. So the developments have been very parallel until about 2 decades ago when the telephone network went through an architectural transformation to become the internet, sorry. So that impact is huge. You started from engineering, but it changes the landscape of multiple industries. The hope is perhaps power network will also undergo a similar architectural transformation in the coming decades. And therefore, a lot of things need to change. Again, we can discuss offline. But one thing that we are interested in is that so right today, if you look at a power network, let's say in the US, 10 to 20,000, small number of large control points. These are the generators that we control. There can be hundreds of millions or maybe a billion endpoints that are just loads we roughly do not control. Hopefully in the future, the situation is almost flipped, that we have hundreds of millions of distributed energy resources, which are PVs, wind turbines, electric vehicles, energy storage, smart buildings, smart appliances, and so on, that are intelligent, that can be controlled. They are not just passive loads. Some may generate, some may communicate, measure, compute, control, and all of that. Right? So that's the kind of network. And in that network, we think a lot of the applications in that kind of environment will require real-time optimization control. And a lot of the computational challenge, one of the computational challenges underlying them is to explicitly or implicitly solve powerful equations, which we saw is difficult. But the network is actually solving that for us for free at scale in real time. And the idea is that whatever you want to do, perhaps we can exploit that. Right? And if we do that, then we will naturally get algorithms that adapt to evolving network conditions. So that's the online, the real-time part for the workshop. So I wanted to give you two examples. One is online OPF, one is fast time scale, but I don't think I will have time for the third part. So we'll just look at the online OPF. OK, so I will also close with this slide. So hopefully at that time, this become clearer what this means. So from the first part, we saw that instead of solving this, you can solve relaxation, which is OK, fine, good. But the traditional algorithm, whether you use it to solve this directly or solve this directly, are all offline, which means you compute until it converges, then you apply the solution. And therefore, it's not suitable for our purpose. But later on, I'll show you some simulations that will compare our online algorithm with this offline algorithm. So we'll compare if you offline solve the relaxation, you check you indeed get optimal solution, and you compare the optimality and the computation time for the online algorithm. OK, so the idea of online algorithm is very, very simple. So if you think about what we can actually do, well, in the physical system, right? So the physical system, there's a model, like what Edward Lee said. And hopefully so what is a model? A model is simply a set of variables and a set of equations. Hopefully, every variable corresponds to some controllable device or some state in the physical network. The point is, in the physical network, we cannot control all state. There's only a set of variables that we can control. And therefore, so these are the controllable devices X and the uncontrollable network states Y. So now we're looking at the modeling part. And therefore, what we can really, the only thing we can do is when we interact with the physical network, we can only change X. The network is going to settle down in something for their Ys. Mathematically, it means that you solve the powerful equations to obtain the Y. That's what it means. Right? So the OPF, you can write it in, say, you want to minimize certain costs. You separate in X, Y, but it doesn't have to be over these two variables, subject to two sets of constraints. One is the powerful equations that we saw, which is simply some nonlinear equality. The second set of constraint is simply some simple box constraint. So this could be, say, the voltage bounds or generation bounds and so on. Right? So simple box constraints. What I mentioned earlier is simply the assumption that suppose the Jacobian of powerful equations is non-singular in appropriate regions, then given any control action X, the network is going to solve this for us and give us a Y of X. So that's the idea. And therefore, you can write the entire OPF just in terms of X instead of X and Y. Right? Then it looks like this. So typically, this is simple, convex. This is all the complexity is. This is simple box constraint. But when you eliminate Y, you get a typically non-convex objective function and then some non-convex constraint. So you can eliminate this one way. You don't have to, but one approach. You can eliminate this by just put this up to the objective function as a through a barrier function. Right? Then you get a complicated objective function as a function of X parameterized by your barrier function over a feasible set that is extremely simple. Supposing instead of solving this problem, let's solve this problem. And again, the basic strategy is very simple, where we can only, when we interact with the physical system, we can only control the controllable variables. So iteratively, we compute the controllable variables as, let's say, one gradient step. Apply it to the network. And then let's assume you can measure everything. You measure all the Y. So the physical network is going to compute, solve the powerful equation, give us a Y. Let's assume we can measure every Y and communicate and compute the next gradient centrally. There's a whole set of issues that in practice you cannot measure every while you may have communication problems. You may have to do it in a digital manner. Let's ignore all of them. And just say, suppose all you do is just this.
But where's the gradient? You have to know that horrible function.
That's right. So the assumption is that you know the horrible function. Yes. Right. So we can discuss offline, right, whether that's reasonable and everything. Indeed. So suppose this is the problem we want to solve, right? Then we just do the simple gradient. You can be fancier, you can do second order algorithms and all of that. Then that's the gradient algorithm. That's what network solve for us. Okay, so what can we, right, okay, so this approach, again, expresses a network as powerful solver. And you will track the changing conditions. So what can we say? Let me tell you a little bit about optimality and then the tracking performance. Okay, so optimality. And the appropriate assumptions is a local algorithm. It's a gradient algorithm. So now, surprisingly, you will converge to a set of local optimum. And if it's a finite, then the sequence itself will converge. Just the standard gradient behavior. So under a certain assumption, the local result becomes global. So there's a certain assumption, and then there's this condition. In other words, next slide, I'll comment on whether the assumptions are reasonable. What the assumption is the following. So P0, Vk's are certain uncontrollable variables. So in the particular, for those in power, this is the real power of the substation. Say we don't control that. So X will all be the intelligent loads that we control, for example. This is the voltage magnitude square at every node K. So those uncontrolled variables as a function of X. If this is convex and this is concave. So these are the assumptions. And then you look at the set A. So X, again, is the simple box constraint on the controllable variable X. And in that constraint, so there's a voltage constraint that becomes functions of X. Right? So the voltage upper bound is this V hat. Suppose you look at the smaller convex combination of lower upper bound. Right? So this is set A. If the convex of local optimal lies in this set A, then the local result becomes global. And therefore, while we can make A arbitrarily close to the original feasible set, are these assumptions reasonable? Then you can show, well, okay, so A is not tiny. A is reasonable. Okay. Otherwise, it's not meaningful. Then are these assumptions reasonable? Well, it turns out for each such function, you can write down a certain OPF. It's a very simple form of OPF. And it's radio network. Right? Then if SOCP for that OPF is exact, then these conditions are satisfied. Now, again, there's no guarantee. But our experience, many other people's experience, is that very often it is exact. And therefore, it's probably not entirely unreasonable assumptions. But of course, there's no guarantee that you will get global optimal. Let's try to estimate the gap between any local optimal and the global optimal. It's not quite comparing global optimal. So the statement is the following. Pick any local optimal. Compare with any feasible point that's slightly away from the boundary. Now, the global optimal can happen to be at the boundary, which is not uncommon. But compare these 2 points. Right? So you look at the cost of any local optimal, the cost of any feasible point slightly away from the boundary. You can bound that. It's a messy expression. But if you look at arbitrary test systems and so on and so forth, this is typically very small. So what it suggests, informally, that any local optimal is probably almost as good as any strictly interior feasible point. I'll show you some examples where it turns out to be good. So that's the first part. So we have some understanding of these optimality properties. The second is tracking performance. So far we have been looking at static OPF. So we have this problem, and you want to solve it in real time, so that you continuously compute decisions for the controllable devices. You interact with the network, and you just compute. And then we know roughly asymptotically how you might behave.
The reason that every time you compute, say an x of t, and you give that as an input to the network, and you observe y of t. The reason for doing that is you can't do this offline computation, or some dynamically network conditions are changing?
Both.
Okay.
So the network condition changing is one big reason. Okay. But also there are applications. Now these are applications that we imagine, right? So these are the future. Applications where you probably have to do in a distributed manner. There's no way you can collect information centrally, solve it until it converges and then dispatch. Okay. Now, of course, the talk here doesn't address those issues because there's a big issue on what if not everything is observable, what if you have to do it in a distributed manner and all of that. But that's sort of the underlying motivation. But the first motivation is, 5 minutes. So the first motivation is tracking is the following. Suppose the network changes slowly. It doesn't have to be slowly. Suppose the network changes. It's characterized by some parameter gamma that changes over time. So this could be low changes or generation, say renewable generation that changes and so on. And therefore, each time t, you get an OPF. And suppose every time you compute a gradient step you apply, then the network changes. You could look at the case where the network changes a slower time step, that you compute 10 and you compute and apply 10 gradient steps, and then the network changes. But let's say the network changes the same speed as your control's time scale. Let's compare the performance of the online algorithm applied here with the optimal solution of here. So optimal solution here means that at each time t, suppose you solve this optimally and globally optimally somehow. And then look at the cost, sum over a certain horizon. Right? So the global optimal is this x star. Right? So, I'm almost done. Okay. All right. Okay. So the global optimal is the x star. So given the global optimal x star sequence vector, you sum over its cost. That's the optimal cost. Probably not realizable. And then suppose we just do the naive first order gradient every time t. You get a yt. The problem changes, but you compute t plus 1, and then you apply it again and so on. Right? So, and then you look at the cost. And you can bound them, and it has two terms. So the structure is that if the OPF problem doesn't drift very fast, it's all intuitive, it's not surprisingly, then the bound is low. Right? So the OPF doesn't drift fast is that the optimal solution from t to t plus 1 does not change much. Then this term is small. And this term has to do with this gradient algorithm, just local algorithm. There's always potential gap between the local optimal and the global optimal. And therefore, if this changes slower than square root t, then the per step regret, so divide both sides by t, then this term goes away. And therefore, if the rate of drifting is small, then the per step regret is entirely bounded by sort of average gap between local and global optimal. So there's probably no way to get rid of this. Yes?
I'm assuming in larger networks the drift will be slower, and in smaller networks will be a larger drift, like on real networks, supposedly. So
maybe appropriately normalized, probably, right? Whatever appropriate. Yeah. Okay, so this is show some simulations. So this is this set of networks with different sizes. This is if you solve as so this in this particular simulation is radio network, it's a distribution network. It's actually multi-phase unbalanced, but that's fine. You can solve relaxation. You can check, you get optimal solution. So you can look at the optimal cost. You can look at the computational time in CVX, and then this is the student Lingwen Gan's own code. Just do this gradient step. This is a static problem, static OPF. The objective function and the computational times, but this is not MATLAB. This is his own code, so it's faster. Just get out of MATLAB. The error is the difference between the objective value, so it's essentially 0, and then the speed up is significant if the network is large. Even though the gradient, the online algorithm achieve essentially the same objective function, the solutions are actually can be quite different. So it means that it's very flat. So, okay, I will stop with the same message. Thank you very much.
Is there any chance of your gradient algorithm being decomposable in any way?
So you can do it in a distributed manner?
Yeah.
Okay, so the short answer is yes, but I think there's a lot of work that needs to be done that we have not seriously looked at. For example, this is a small piece of his thesis. So we're just starting on this online OPF. In this example, he actually did it's not only the multi-phase unbalanced network, it's actually distributed algorithm. But his distributed design is not simple. It's quite messy. So I think there are a lot of work that still needs to be done to have a nice, clean distribution.
If the optimal solution is quite flat around, then can you do something that's decomposable? It just gets you into the interior and then.
I see. That we haven't.
Something simpler.
Right. Don't know. Yes.
Thank you very much for your presentation. As I can see in these simulation results, as the network becomes larger, the speed gets more faster. Generally, the trend is like that, right?
The speed up, or
yeah,
yes.
Speed up is much. Why is the reason?
Not clear.
Is it a general trend, or it's just?
It could be the. I guess one can look at whether this scales at a faster rate than this. But this is local algorithm.
Yeah. And the other question is, I think it would be interesting that your comparison of online solution to the linear, current using linear optimization, and compare their speed, because currently the main reason why I think utility companies stick to their linear is the speed. So when you compare with Convex CVX, it's much different, right? The speed. And when you compare to linear, you can see you can much more sway them.
Right. So for this particular set of, so this is actually one of the real networks in SE, and therefore we have done a lot. For this particular set, we did look at if you solve the linear problem, but not using DCOPF. DCOPF is not suitable for distribution systems, but Barang-Wu's original model actually has a linear, so we did use that. The result shows that because for this particular network they have is the loss is low, is sort of overbuilt, and therefore the objective function between the linearized and the Barang-Wu's, the nonlinear, is small. The computational time, this is significantly higher than if you just solve the linear.
Oh, thank you.
So, you know, I mean, most people have sort of a libertarian fantasy that we'll all have solar panels on our roofs, and you know, and basically can go off the grid. And in that nirvana, in quotes, there's nobody. Who's doing the optimizing, the distribution side?
Right. Right.
And I know that nirvana is ridiculous. Of course, there will be somebody
right.
managing the system.
Definitely.
What's the most important optimization problems then on the distribution side?
So, right, okay. Again, there's a lot of discussion, but let me give you one example, which is a real example. This is a startup, very, very, very interesting startup that uses Tesla battery pack to provide two services. So they have two revenue streams. One is to reduce the demand response for buildings. One is actually provide demand response for SCE. Now one can imagine that, so they can, in the future, work with SCE to jointly optimize not only their storage, but also some assets on the grid, distribution grid, for example. You could imagine you have community solar stuff that you can, or aggregators, that jointly optimize that with grid assets and so on. But again, all these are future scenarios. But
a quick question. The loads on the grids, either on the backbone or even distribution level, especially distribution level, must be highly periodic. On a daily basis.
How variable?
Yeah, it's almost periodic, right?
Well, it depends on what aggregate level. Yes, at the aggregate level, at the very aggregate level, it's actually quite predictable today. In the future, it depends. Level of the city.
Small city like township.
Right.
It's still quite highly periodic. It's certainly true for all the.
Depends a lot on the temperature, but yes,
like
it's quite. Yeah.
Transportation that I was showing is super periodic, very, very highly periodic. Okay. So then small fluctuations there. So could you do something about like solving this, I don't know, for a month and then having sort of look up data to see your initial starting points?
Right, potentially, but just on the periodic side, let me show you real data too. Do I have it? Here.
Don't forget the supply, the wind and solar could be.
Right. I think it depends. Probably depends on the applications. One, you might be able to do it. One might require much faster timescale adaptation. So so this is a set of one graph for each day. Just look at the upper graph. So this is the EV charging. This is the real EV charging at Caltech. Is it very periodic? Somewhat, but there's significant variation. Now, what is the optimization here is that if you optimize, you can, instead of doing this, you can squash it. So the P, the lower the P, the better. And therefore, for this assumes 1 minute update.
Okay, thank you very much.
Thank you very much.